Welcome everyone to the 2022 State of the Sound Symposium. This symposium will be presented in 3 sessions. When scientists seek to understand how a natural system works, they look at the different levels of scale that are observed in it. The talks in our first session provide a large-scale view of the Port Royal Sound and patterns of change that have been observed in its watershed. Our first presenter is Dr. Will Doar, Senior Geologist of Coastal Plain at South Carolina DNR Geological Survey, and he will introduce us to the geology of Port Royal Sound.
Thank you very much, Chris. This talk was put together. It was a shared effort between me and our coastal geologist, Katie Luciano, also with the South Carolina Geological Survey. And I thought I'd show a great big cup of coffee to get everybody started this morning in the slideshow presentation. I'll break this up into the 3 most recent major events for our area. And we'll start with event 1, the building of the Appalachian Mountains. Now, we have billions of years of Earth history before this point. But really, this is just focused on what directly affects what we're standing on when we're in the Port Royal Sound area. So the Appalachians were built around 320 million years ago. And then the Atlantic Ocean started to open by the separation of North America, Europe, and Africa about 180 million years ago. And after the opening of the Appalachians, there was a major shedding event during the Cretaceous. And what I mean by shedding event was major erosion on these newly built Appalachians, pouring sediments down into the hole that the opening of the Atlantic formed. And so we have a large wedge of Cretaceous age sediments along the coastal plain. And then we have a thin veneer of what we're actually walking on the very top. And that's what we're looking at is post 65 million years ago is most of what we see today, excuse me, on the surface. So when the continents tore apart to form the Atlantic, they left a series of embayments and promontories along the coast. The Albemarle embayment sits under the Pamlico-Albemarle Sound system. The Cape Fear Promontory, which is also the Cape Fear Arch, is here near the North Carolina-South Carolina state line. And then you see there's another embayment, the Southeast Georgia embayment, and that's directly underneath Port Royal Sound. And then the next promontory is the Arch system here in Central Florida. And this system of embayments and promontories forms a sawtooth pattern that is actually mirrored on the other side of the Atlantic. So these actually tore apart just like undoing a zipper. If you look in the lower left-hand corner, you can actually see that this sawtooth pattern actually controls the elevation of some of the geology along the coast from Florida north to North Carolina. We come up out of South Florida over the first promontory, and then following the Trail Ridge, which is a prominent feature in the Georgia that is correlated up into South Carolina and North Carolina. You can actually see that it drops in elevation and then it picks up again as the Orangeburg Scarp back in elevation here. And these transitions right here for the Orangeburg Scarp portion can actually be seen here on this structural features map. And this is a map of all the faults that are recognized from remote sensing under the coastal plain of South Carolina here. And this is the northern edge of the Southeast Georgia embayment here. This east-west line with the little tooth pointing south in the embayment. Now, Spring Island is down here, and here's Broad River and Port Royal Sound here, and Whale Branch and St. Helena Sound here. And this is the Garner-Edisto Fault. And this is an older map, so this line may actually nowadays, from what we know, might be scooched north just a little bit more. But the fact that there's this major fault related to the formation of the embayment controls much of the sedimentation pattern here in this area. It specifically controls the orientation of Whale Branch, which is not the same direction as most of the other rivers in the region. And if you notice, the trace of the possible new trace of the fault up here intersects the headwaters of the Broad River. We don't know what that means yet, but it's something we look forward to trying to figure out in the future. Now, the other thing about this is that when this is torn, generally there's a hole left here. That's why it's called an embayment. But in the Beaufort, Port Royal, Coosaw, St. Helena Island area, it turns out that there was a reversal of motion on this fault, maybe in the last couple million years, that resulted in deeper sediments being brought up to the surface. So I'm going to start walking us through time, and that'll become an interesting part of the story in just a moment. So here's the Eocene. The Cretaceous is down off the bottom of the time scale. And then we work through the Paleocene and then into the Eocene. The Paleocene is an interesting event on its own, but it's generally so far down in the pile of sediment. There's 3,000 feet of coastal plain under Charleston all the way down to hard rock. So there's a tremendous pile of geology down there, but we're really only influenced at the surface by the last little bit at the very top. And the Eocene was actually brought up even closer to the surface on that fault that I was talking about. The Eocene deposits along the coastline resembled the Florida Peninsula and the Bahama Banks down here. They were carbonate sediments. The Santee limestone, the Harleyville limestone, the Lazaretto Creek limestone just across the state line in Georgia are all part of this Eocene age system. And here's millions of years on the left-hand side, from 55 million years to 35 million years here. That Eocene material has been actually rotated up and closer to the surface, and under the Marine Corps Air Station in Beaufort, it's actually right at sea level, as well as close to sea level under Coosa Island in the north end of Ladies Island. And the reason why that is important is here is the town of Port Royal. And you see the new arch bridge going out to Ladies Island on the east side of the picture. And the lower left side, the southwest corner of the picture, you'll see the road going down for the Paris Island Gateway to the Marine Corps Recruit Depot. And so this is the town of Port Royal. And if you look kind of center and left, you'll see a green bean-shaped feature. And then there's some dark blobs down here. Believe it or not, these on this LiDAR image can be seen much clearer are sinkholes. And that is because that lime is so close to the surface, it's easy to dissolve, and then the overlying materials collapse into it. So we do have sinkholes and karst topography in South Carolina, not like they do down in Florida to the same extent, but many of the small wetlands, the little wetland parks down here in Port Royal, this green grassy savanna field here, and maybe some of these features out on Ladies Island are sinkholes related to that limestone being brought so close to the surface. And what I mean brought close, north of Whale Branch over at Edisto Beach, it's several hundred feet down to that lime, whereas in this area, it's really close to sea level. So now we'll move to the next interval of time, the Oligocene. This is what most people think of as the Cooper Group section in the Charleston area, or the Ashley Formation, Parker's Ferry formations. And this was where we transitioned from a carbonate platform to a continental shelf platform. And so the sediments get much finer, the water depth increases, and we have much more nutrients, a higher concentration of nutrients brought in due to upwelling of the deep ocean waters coming up the edge of the continental shelf. Tremendous amount of phosphorus was brought into the system. And this phosphorus is what is related to shark's teeth you find being black. Some of the old bones that people find when they dig new mines or lagoons for development stuff being black. It's the phosphorus that's brought into the system. And this unit is eroded in some places and preserved in other places. The Oligocene, for example, is not well mapped underneath Port Royal, but is well mapped underneath the Charleston area. So it really depends on where you are as to whether or not you have direct contact with it. But in the places where it has been eroded, those bones and teeth that everybody loved to find, are often incorporated into the younger overlying sediments like the Miocene here, which is the last 22, which was from 22 million years to about 6 million years ago. So much of that stuff was reincorporated into the Miocene, and the Miocene was a similar environment to the Oligocene, where there's a warm, shallow continental shelf sea. Once again, high bioproductivity, so high nutrient loads in the system. And this is where everybody's favorite shark's tooth, the megalodon, came from. The great big shark's teeth that everybody loves to find was from this period of time, from this warm, shallow sea. The phosphate mine up in North Carolina is mining material from this interval of time. The phosphorus wasn't necessarily originally in the sediments that were deposited, but in the pore waters that were brought in, the phosphorus can get entrained with the organic materials. And that's why everything's black when you find these fossils. If you were to look at the same age fossils from across the ocean in, say, Morocco, they're all tan because they didn't have this type of phosphorus load put into the system. So this is where the really cool shark's teeth that everybody loves to find come from this interval. The Miocene is also the first good confining unit when you're thinking about aquifer studies. So everything younger than the Miocene is pretty much open to anything that pours on the ground locally, goes straight into that interval of water. The Miocene here is very fine, continental shelf, very clayey, acts as a good block to the underlying water, the underlying aquifers that many people get their drinking water from wells from. Now I'm going to move into the younger material. These are big swings, big changes over long periods of time. Now we'll move to the Pliocene and Pleistocene. So we're only talking about the last few million years now, last 6 million years or so for these two intervals combined. The important thing about this is before this time, sea level appears to have had very large, very slow swings in height. During the Pliocene and Pleistocene, sea level came and went much more frequently and much quicker. What you see on this image is the current shoreline here from the green to the blue. In the Pliocene and Pleistocene, sea level has gone all the way from right here at the Orangeburg Scarp, or if you're on I-26, exit 145, all the way out to the edge and just off the edge of the continental shelf. So sea level swung both back and forth between these two boundaries during this time, at least 80 times during the records that they are able to pull out of the deep ocean where this is preserved. Now, it doesn't mean it went all the way across this interval. Sometimes they stopped short, sometimes they went all the way across. So we don't have all of these preserved in South Carolina, especially not in the Port Royal area, because it is, as you see here, here's Broad River and Port Royal Sound. It's only in this interval right here, but massive swings of sea level across this area. So how do I get to understanding what we're looking at today and sharing it with you? Well, first off, we look at the modern. This is a cross section through a modern beach system with the Atlantic Ocean, beach face here, low tide bar, nice dunes here, the beach ridges, backwater ponds sometimes they're just the low areas, the swales between dunes. Sometimes you get a nice back buried dune field and then the salt marsh behind it. Well, as it turns out, this has happened over and over again through time, and these can be stacked against each other. All of these are different ages, but they're all basically this exact same geometry. Here's a more detailed example of it from a publication we have. Here's the ocean here. Sea level is rising. It is building a marsh system here and building the Bear Island. And as sea level rises, it pushes this inland as it climbs this slope here, this scarp, which is the older materials. You can think of this area right here as being that area on that one, this area on this one, this area on that one, this area on that one. So this is a prettier, more cartoonish way of seeing it. This is a real world example here on the bottom right. The Latson Formation on the left is older. The 10 Mile Hill Formation on the right is younger. And using these vertical lines here, these are actually places that we drilled and retrieved the materials to examine them to prove that this transition to that transition happened and with this geometry. So, and here's how we did it. Here's the Geological Surveys, South Carolina Geological Surveys, older drill rig. And we use augers, which are giant corkscrews, to drill into the ground and bring materials to the surface for geologists to examine. And there is a hand lens or jeweler's loop here being used to look at some of the material that came off these rods. Those last pictures were on Hilton Head Island. This drilling's on Defusky. So we can actually get this drill rig out in interesting places to go collect these samples. And here's an example of how we know those things are stacked. This is a freshwater cypress swamp deposit here. These are actually cypress stumps. They are now covered by Spartina alterniflora marsh. Here's an older marsh that may be 100,000 years old, and the new marsh sitting on top of it. We use all this data to produce these type of models in cross sections. So we do this over and over again. Sea level comes up, sea level goes away. Sea level comes up, builds the next one. Let's say it's not the same height, it's a little bit lower. It preserves everything here. You repeat this over and over again, sea level up, sea level down, sea level up, and eventually you end up with all these stacked systems, all beaches, bare islands, salt marshes, all next to each other, but all different ages. Now, this black and white picture doesn't look real pretty, so let's make it really colorful. There's essentially the same diagram, just in pretty colors, because colors help maps. So here's the map of the coastal plain of South Carolina going almost to the Orangeburg Scarp. And these colors are basically the same as that cross section. So here's the modern. The modern gives us an idea of what to look for in the older stuff. We look for the evidence of changes in the drilling, and you can produce a map like this. And once again, Broad River, Port Royal Sound down here. So here are the results. These are much messier maps compared to the simplified one you just saw. But here's Spring Island. And then you see Hilton Head Island just south of center of the map. The town of Bluffton here dead center in the left-hand map. Defusky in the southern portion of the map. Palmetto Bluff kind of in the southwestern portion. In the right-hand map, you have St. Helena Sound with Edisto Island in the northeast corner, the Dale area in the northwest corner, and then St. Helena Island and Beaufort here basically in the center. So this is a much more complex map, but this is the result of the detailed work and the mapping that we've done over the years. And other geologists come up with similar maps for other areas. So what's important to see about this is the preservation of that material every time sea level comes and goes is really messy. There are not, except for the northwest corner of the left-hand map, which is actually related to the Savannah River and not the actual beaches coming and going. Tidal creeks, major rivers, all of these things can remove this material, but they build space for new salt marshes every time they remove the existing materials. And then every time there's a low stand where sea level falls, then all the rivers and creeks can actually cut deeper, make room for more changes when sea level comes back up again. So these are available if anybody wants to see them and study them in more detail. But this is a record of sea levels, in this case, for the past 200,000 years. I won't go into the really fine details at this time, but you're welcome to ask plenty of questions later. And I want to thank you very much. And here's some follow-up materials if you're interested in more detailed information of some of the deeper materials in surrounding areas, or just our detailed maps. Thank you.
Thank you, Will. That was great. one of the things I want to share right now is that there will be follow-up materials, and this material will be available online as far as getting these references. So you don't have to be writing very quickly as we talk right now. We have time for a few questions if there are any. I'll start out. Can you explain how you recognize that you're at a boundary between one terrace, I believe you called it, versus another terrace? In other words, these are areas where the terraces were created when it was the sea level had gone out and back. Is that what you're saying?
Yeah, this could be an hour-long discussion on its own, so I was trying to simplify it. What we try and do is recognize that change in pattern from those cartoons, where you end up with a salt marsh behind a beach. And then the sea level drops, and if everything goes well, that beach and marsh are preserved right there where they were as sea level goes out. When sea level returns, if it doesn't get high enough to obliterate that pre-existing material, that next package of marsh and beach will slide up against it, and you'll end up with the marsh right against the beach. So you can look for the inland marsh, the seaward beach, that pattern repeating as you work from inland towards the coast. So you know when it changes from pretty beach material into good old mucky salt marsh material that something has happened. And then you just need to look at where it is, because it's extremely unusual to form a marsh in front of a beach. So you're looking for that geometry at the surface first, and then drill the holes to chase that geometry into the subsurface to see if it does all swing down towards the coast also.
Okay. Question by one of our observers is, how has sea level changed over the past 20 years in the area? Do you have any information about that from a geological perspective?
The local sea level rise, we have to deal with what happens on a local scale. Global scale things may drive sea level changes, but the land also can react to additional water or less water, or stresses in the crust that can warp land up or warp land down for subsidence or uplift. So we deal with the relative sea level rise, which is whatever the combination of factors that is. The Charleston tide gauge does have data that supports that local relative sea level rise is occurring on a couple of millimeters a year. So when you add more water to the system and raise the local elevation, the water is going to wet more of what we think of as the dry land. And the two most obvious things I can think of is when you wet more dry land, you change the species from upland species to salt marsh, salt tolerant species on the ecological side, but you also give more opportunity for water to act on the uplands. And so you can actually increase local erosion by having waves reach higher up onto a bluff, or more water moving through a creek to make a creek larger and eroding the creek banks.
Right. Okay. Very good. Thank you.